Here's our last lesson for this chapter, chapter 9.3. Here we're going to be exploring solving questions by solving both algebraically and graphically. And I just want to remind you that in the final exam, in the provincial exam, they will be asked, you will have an opportunity if you want to solve questions using a graphing calculator, but it is not required for the exam. So when they have a graphical question, really what it comes down to is either fairly easy questions like the one we have coming up, or where they might have you explain how to solve graphically, and we've done those types of questions before. So what we'll do here is we're going to solve the question that we're given here algebraically, and then we'll solve it graphically, and then we'll answer the questions on the bottom of the page there. So algebraically, what I'm going to do is find out for what value of x is that a true statement. So if I say, I'll just rewrite it to get started in this area here. To solve for x, I want to work with the left-hand side until I just have an x by itself. So I'm going to add a 1 to both sides. So I have 1 over x plus 2 is equal to 4. Now what I will do is, since I have an x plus 2 in the denominator, if I multiply both sides by x plus 2, then on the left I just have a 1 remaining, and on the right hand side I'll have 4 times x plus 2. If I multiply out that 4, I get 4x plus 8. Now if I subtract 8 from both sides, I get negative 7 is equal to 4x. Dividing by 4, I'll get x is equal to negative 7 over 4. And yes, it is that easy. So there is my algebraic solution. So now let's explore the graphical solution. So there's really, if you recall, there's two ways to do the graphical solution. And this is the first way, probably the easiest way, is take what's on the left-hand side of the equal sign and equate it to y1. So I'm going to say y1 will be 1 over x plus 2 minus 1, and our second function, maybe I'll pick a different color, would be what's on the right hand side, where y2 is going to be equal to 3. So first of all, hey, the y2 equals 3 is a pretty easy one to graph. So that one would be wherever y is 3, and x can be anything. So I get a horizontal line that looks like this. So this is my y2 is equal to 3. My other one isn't really that not too tough either. I notice here I've got a vertical asymptote where x is equal to negative 2, and I have a horizontal asymptote at negative 1. So I'll put that in. So at negative 2, I'll draw my asymptote here. And my second asymptote where at minus 1. And now if I take a look at it, I'm going to be looking for values that multiply out to 1. So in particular, I'm interested in where these two lines are going to meet. So 1 and 1 would work, a half and 2 would work, and then also a quarter and 1, 2, 3, 4. So it would actually hit right there. But let me just sketch out this line. And here down below. So there in blue is my y2 is equal to, y1. y1 is equal to 1 over x plus 2 minus 1. So the point at which they intersect is what we're interested in. So this point right here, and you'll recall when I found that point, I'm going over 1, 2, 3, 4 up from the intersection of the asymptotes in order to make it multiply by into 1, 4 times a quarter. So I'm going, the x value of that intersection is what I'm interested in, and it is negative 2 and then plus a quarter. So because this vertical asymptote is at negative 2 and I went to the right 1/4 of that, so if I was to put that together, I guess that would be negative 8 over 4 plus 1 over 4, which would be equal to negative 7 over 4. Okay, something I want to remind students of is that To find the graphical solution here, I guess the steps that you can say in words is, equate y1 to the left-hand side of the equal sign, equate y2 to the right-hand side, and the solution is the x value. Oops, I need to spell value. Value of the points of intersection. Point or points. In this case, there's just one. Points of intersection. So in this case here, my answer is -7, 4. My solution is not this point. My solution is the x value of that point. Okay, so looking at the bottom here, it says explain the relationship between the roots of the equation and the x-intercepts of the graph. Okay, so I think that what this question on the bottom is referring to is that there are two methods to finding a graphical solution. This is kind of like method number one, where you equate the left-hand side with one line and the right-hand side. But you could also say the second sort of graphical method, and we've done this earlier in the course, is to equate this whole thing to 0. So it'd be 1 over x plus 2 minus 4 is equal to 0. So looking at my original one, if I was to add or subtract 3 from both sides and turn this into a 0, then I would get a -4 instead of that -1. And then to turn this into a function and say y is equal to 1 over x plus 2 minus 4, and now I would just graph this function. And this isn't even that hard of one to graph. Let me just think about what it would look like. I would have a horizontal at -4, right, -4, and I would have a vertical asymptote at -2. And it would be a very similar looking graph to the one I wrote, except it would just be down from where this original graph was, instead of the graph being at, having the horizontal asymptote at -1, it'd be at -4. So my graph would end up looking kind of like this. And the place that it would hit the x axis would be my solution. So to get back to this question here, this x value is going to be our same answer. It's going to be that -7 over 4. So to go back to explain the words here, it says explain the relationship between the roots of the equation. So the roots of the equation is, when is this equal to 0? When is this true? The root is -7 over 4. And the x-intercepts of the graph, so the relationship is that they are the same. So you can find the roots of an equation, and that will give you the x-intercepts of the graph. We only have one more example. This is a fairly quick little lesson here. And again, we're going to do the same thing. We're going to solve this algebraically, and then we'll solve this graphically. And then I will basically tell you that there's not too much more to do in this unit. So algebraically, what we're going to do is we're going to solve for x. So if I have an x on either side here, what I'm going to do is multiply both sides by x minus 1. So I have 2 is equal to x minus 1 times x minus 2. Now when I multiply that out using FOIL, I would get x squared minus 2x minus x plus 2. So I will get x squared minus 3x plus 2. So now if I were solving here, I would subtract 2 from both sides. So I will get 0 is equal to x squared minus 3x. When is that statement true? Well, it becomes even more obvious when I factor the right-hand side. And so when will x squared minus 3x be equal to 0? Well, when either x is equal to 0 or when x is equal to a positive 3. So those are my two answers. So I was solving that for x. So algebraically, x equals 0, x equals plus 3. Graphically now, same idea as before. I'm going to make the left-hand side, so 2 over x minus 1 will be my first line, and my second line will be x minus 2. You know what, I'm going to start with my x minus 2 because it's a bit easier to graph. It has a y-intercept of negative 2 and a slope of 1. So starting at negative 2 and a slope of 1, so it's going to hit all those little intersection points. Oh, there I go. So something like that. And now for the other, back to green, I will have a vertical asymptote at x equals 1. And my horizontal asymptote will be on the axis at y is equal to 0. And now looking at where the two asymptotes meet, I want to pick numbers that multiply out to 2. And particularly I want to pay attention to where it's going to hit that x minus 2. So starting from here, 2 and 1, bingo, I'm going to get that one right there, 1 and 2. And so my basic sketch is going to be looking something like that. Didn't do a very good job of hitting that point. So this is the point 3, 1. Over here, I'm looking for pairs of numbers that multiply out to 2, so 1 and 2. So again, I'll be hitting that spot and this spot, and so my sketch will look something like this. There we go. And this point here is 0, negative 2. So my solution is, once again, remember, it's not the points, it's the x value of the points. So my solution is this 0 and this 3 here. So I'll just write it out. Solutions x equals 0 and x is equal to 3 is my answer. Okay, so I hope that is enough of a solution for you. There is the homework pages, and I just want to mention that in the rest of our work here, oh actually, yeah, I have one more thing to cover, but before I get to that, I'm going to mention that we can not worry about the oblique asymptotes. That will not be covered in our course, so apology for photocopying that and wasting a little bit of paper. And I'm thinking instead of using this review, if you indeed have a copy of this review, if this was photocopied for you as well, I would prefer if you use the two other reviews, the exam review and the test bank review, rather than going through this one. So I don't want to, again, maybe in the future I won't photocopy it. I would like to do one example here of an inverse function, and this was a bit of a surprise for me when it came out in the last provincial exam. I think it was the January of 2015. So I want to cover this, and I will give you a question like this on your 9.3 mastery check. So I will be giving you similar to this, I'll give you a y is equal to f of x, and your question will be to sketch the graph of y is equal to 1 over f of x, which is known as the reciprocal. So what does this mean? Essentially what you're going to do is look at a number of points, and I'll kind of label some interesting points for us to consider. Maybe a large one up there and a large one down here. And you want to keep the x values the same, but find reciprocals of your y values. So remember, if what are reciprocals? The reciprocal of 1 is 1 over 1, so it's still the same. The reciprocal of 2 is a half. The reciprocal of, say, a negative 1/4 is going to be negative 4. So this is how reciprocals work. So let's try a few examples. Maybe I'll clean up my workspace here, and we'll try to make a table first of x values, and then we'll say, well, what was the y value for f of x, and then what would be our new y value for 1 over f of x. And I have a few interesting points here. So maybe the first one we'll look at is this one right here. So here is an x value of 0. And for my original function here, y is equal to f of x, it looks to me like I have a negative 1 for my y value. So this point is 0, comma, negative 1. In my new function here, the reciprocal of negative 1, so that's negative 1 over 1, is still going to be negative 1. So my answer here is that that point stays the same. And you're going to notice a pattern, if you remember this from grade 11, is that we call that an invariant. So wherever it's negative 1 or wherever the value is positive 1, it stays the same. Now let's do where x is equal to 1, and here the y value for my original function is 0. So my y value for the reciprocal function, which I'm going to be graphing, 1 over 0, is also equal to 0. Now looking at when x is equal to 2, my original function, the value is plus 1. The reciprocal of plus 1 is also plus 1. So far, all 3 points are exactly the same. Now, what makes things different, however, is let's say if we picked a point in over here. Okay, so maybe I'll pick it at, what would that value be? Maybe for x, maybe 0.5. In my original function, I might get something like, I don't know, 1/4. Negative 1/4, I should say. And so my reciprocal function is going to end up being at negative 4. I would get a very large value. And then as I get closer and closer to this value here, I'm getting a smaller and smaller negative value, and which would cause a larger and larger negative value for my reciprocal. So you see this feature of how it works. Now this is where we can graph onto it. Oh, you know what? I made an error. The reciprocal of 0, 1 over 0. I wonder how many people were jumped in their seats when I said the reciprocal of 0 is 0. 1 over 0 is undefined, and that's where we get a vertical asymptote. Sorry about that. So we get a vertical asymptote right here. And we're used to the vertical asymptotes. We're used to a vertical asymptote, you know, either having a shape that comes down like this or like this or things like that. And so, yeah, we're going to have that again here. And just to the left of it, we have a very small negative value. And that's why we get this large negative, because it's a reciprocal. And it will hit this spot here, and we just discovered that earlier because the reciprocal of negative 1 is negative 1. Coming to from the right-hand side of that vertical asymptote, just to the right of positive 1, here in the original function we have a very small positive value, so the reciprocal is going to be a very large positive value. So you come down and you'll hit this point right here. So that's the important point. And then from here on, the original value gets becomes a very large negative, so this gets closer and closer to 0. So we end up getting this kind of a function, and we get this kind of a function as well. So that will be, here maybe I'll try to make it a little bit darker. So this will be our answer there, and this is our answer there. If I scroll down, this is the way the marks were for the marking guide. You get a mark for the vertical asymptote, so you need to draw in the vertical asymptote, and you get a half a mark for the general shape to the left and for general shape to the right. So as I said, I'll give you you know, another sort of similar one to this, and I'll say, can you please draw the reciprocal for it? Okay, and like I said before, I wouldn't worry about doing the oblique asymptote or that review afterwards. Thank you very much. I will see you in class.